Hello students, welcome back. In the context of solving non-linear programming problem, the Hessian matrix plays a crucial role in determining whether a critical point of the objective function corresponds to a relative maximum, minimum or saddle point. Saddle point means which is neither maximum nor minimum. This is the Hessian matrix which is denoted by H. Here suppose your objective function involve x1, x2, x3 in this way xn variables, decision variables, then Hessian matrix can be defined as this is a first row first column. We are going to differentiate f with respect to x1 twice, or you may write it dou square f upon dou x1 square. Similarly, this is a double derivative of f with respect to x2 and then x1. In this way, we can differentiate f with respect to xn and then x1. Okay, so we know the partial derivative. We are here not going to give too much time for this derivative, as an when example will come, it's a very easy process of finding the Hessian matrix. To determine whether a critical point is a relative maxima or minima or saddle point, we examine eigenvalues of the Hessian matrix. There are two ways. I will explain both the ways. In the first way, with the help of eigenvalues, we can say whether the function is maximum or minimum at the critical point. Second way is by using its principal minors. Okay, first is with the help of eigenvalues. If all eigenvalues of a Hessian matrix are positive, then the critical point corresponds to a relative minimum. And in the other case, if all the eigenvalues are negative, then the critical point corresponds to relative maximum. Saddle point. If the eigenvalues of the Hessian matrix have both positive and negative values, means mixed, then the critical point is a saddle point. So if eigenvalues are positive, some of them are positive and negative, then the nature of the critical point cannot be determined whether it is maximum or minimum using the second derivative test, and additional tests or methods may be required to solve these type of examples. Suppose the Hessian matrix is like this: 2 0 0 0 2 0 and 0 0 2. Now here, if you find the eigenvalues of first matrix, which is 2 0 0 0 2 0 and 0 0 2, we know that if the matrix is a diagonal matrix, then eigenvalues are diagonal elements. So 2 2 2. Here all the eigenvalues are positive. Now, in case of second matrix, if diagonal elements are -2, -2 and -2, so these represents eigenvalue. So here all the eigenvalues are negative. In the third case, suppose here if you find the eigenvalues of this matrix using our standard formula, which is trace is -6, then SMD is equal to here 4 plus 4 and 4 minus 1 3, 11, and if you find the determinant 2 into -2 into 4 and -1 into -2, so this is -8 plus 2, which is -6. And if you find the eigenvalues here, all the eigenvalues are negative. Okay, so if all the eigenvalues of the Hessian matrix are positive in the first example, then the critical point corresponds to relative minima. So all these we are going to cover in the help with the help of example. So here Z is minimum at x naught. Okay, and we will get the minimum value of the function. In the second part here, all the eigenvalues are negative. Then we will get here Z is maximum at the critical point x naught, and we will get maximum value. In third case also, we will get Z is maximum. Now the same concept I'm going to define with the help of the principal minor. Okay, so this is minor of order 1. This is a minor of order 2. So here 2002, and the whole entire matrix is a minor of order 3. Now if you simplify, if you find the determinant of this A1, which is 2, determinant of A2, which is 4, and determinant of this A3, which is 2 into 2 into 2, which is 8. Okay. So since all the values of the determinant 2, 4 and 8, since all these determinants are positive, therefore Z is minimum at x naught. So this is the another way of defining whether the function is maximum or minimum at the critical point. Second example is this. The same example I have carried over here. So here A1 is minus 2. If you write A2, which is minus 2, 0, 0, minus 2, and if you write A3, that is the whole matrix, minus 2, 0, 0, 0, minus 2, 0, 0, 0, minus 2, and if you find the determinant of this, which is negative 2, then positive 4 and negative 8. So these are the values starting from negative value, negative, positive and negative, alternate negative, positive and negative. So here the values of their determinants are negative 2, then positive 4 and negative 8. Okay, negative 8 here. Yes. So if since all the values of the determinant are alternatively negative, positive and negative, then we can say that the Z is maximum at x naught. Okay, so this is the another way you can define with the help of eigenvalues or with the help of principal minor of the Hessian matrix. This is the third example. Same again in case of third example, here eigenvalues are minus 2, 4 and minus 6. So negative, positive and negative. Since the values of the determinant are alternatively negative, positive and negative, then Z is maximum at x naught. So now it is clear that from the Hessian matrix, with the help of eigenvalues or with the help of principal minor diagonal elements, we can identify whether f is maximum or minimum or saddle at the point of stationary point or critical point. Now let us solve this example here. You can remember there is no constraint here. Okay, so obtain the relative maximum or minimum if any of the following functions. So they have given z. So procedure is we have to differentiate this z with respect to x1 first. So if I differentiate this z with respect to x1, which is 2x1 minus 2 minus 4, this is the derivative of z with respect to x1. Then you can differentiate this z with respect to x2 also, which is 2x2 minus 8. If you differentiate z with respect to x3, then you will get 2x3 minus 12. Then to find critical point, you need to solve the equation dou z upon dou x is equal to 0, dou z upon dou x2 is equal to 0, and dou z upon dou x3 is equal to 0. If you solve these three equations, we will get critical point. So first equation represent 2x1 minus 4 equal to 0. So x1 is equal to 2. Second is 2x2 minus 8 is equal to 0. So x2 is equal to 4. And third is 2x3 minus 12 is equal to 0. So x3 is equal to 6. So here your x naught, which is x1, x2, x3 is 2, 4 and 6. Now we will find the Hessian matrix H. Let us calculate the Hessian matrix. Hessian matrix, it's very simple. Here the element which is going to come, we have to differentiate dou z upon dou x1 with respect to x1's again, double derivative. So if I differentiate 2x1 minus 4 with respect to x1 once again, here you will get 2. And the same equation, if I differentiate with respect to x2, there is no element which is 0. Third, there is no element which is 0. So in this way, your first row is 2, 0, 0. Similarly, if you differentiate the second equation with respect to x1 first, here it is 0. With respect to x2 is 2. With respect to x3 is 0. Now you can fix the third equation and differentiate with respect to x1. Answer is 0. With respect to x2, answer is 0. With respect to x3, answer is 2. So this is the Hessian matrix. Now from the Hessian matrix, just now we have seen here all the diagonal elements are 2, 2 and 2, and this is diagonal matrix. So its eigenvalues are 2, 2 and 2. All the eigenvalues are positive, so you can say that this Hessian matrix is a positive definite. And we know the condition. If Hessian matrix is a positive definite, then we will get Z minima. Okay, so Z is minimum at the stationary point, which is stationary point is 2, 4, 6. To get the minimum value of the function, you can put value of x as x1 as 2 in the given z. So this will be 2 square. Then x2 is 4, 4 square. x3 is 6, which is 6 square, minus 4 into 2 minus 8 into 4 minus 12 into 6 and plus 100. So if you simplify this with the help of calci, you will get the answer 44. So value of the function is 44, which is minimum value at the stationary point, which is 2, 4, 6. So this is the first example we have discussed. NLPP first example without constraint. Thank you.